Hello, you're listening to the Science of Everything podcast, episode 127, Weathering, Erosion, and Rivers. I'm your host, James Fodor. So this episode marks the start of a probably 3-episode series where we're going to talk about various processes of weathering and erosion. And that might sound a little specific, but actually this encompasses a wide range of processes that are sometimes characterized as geomorphology. So basically this is explaining the structure and shape of the different landscape features on Earth. And this includes rivers, deserts, glaciers, coastlines and coastal processes, as well as hills, mountains, and so forth. So this basically will look at a range of the mechanisms that give rise to these different features and how they change over time. In the first episode, we're going to be talking about weathering and erosion in general terms, and I'll also talk about mass wasting, and we'll talk about rivers and streams. In future episodes, we'll look at wind processes in deserts, oceans and coastal processes, as well as glaciers, rainfall and surface runoff, and some other aspects of this as well. Recommended pre-listening for this episode is episode 74, Minerals and Rocks, which will give some general sort of background information. To get started, I want to give a little bit more background as to sort of what the topic is that we're covering and how this fits to other things that we've been talking about. I have produced a number of episodes covering aspects of geology, so particularly the study of the production and movement of Earth's crust, the different layers of Earth, like the inner and outer core and the inner and outer mantle, and the tectonic cycle and the production and movement of tectonic plates, volcanoes, earthquakes, and all that sort of stuff. All of these processes are ultimately powered by the leftover energy of the collapse of the Earth and the formation of the Earth at the time of the formation of the solar system, the residual geothermal energy that still powers the movement of continents and the tectonic cycle. So those processes are constantly producing new crust and moving crust around and moving plates and thrusting up mountains and so forth. So those you can think of as sort of internal processes powered by geothermal energy, which is left over from the formation of the Earth. At the other extreme, we've also talked about the atmosphere, and we've done a few episodes now talking about the interaction between the atmosphere and also the oceans, but particularly the movement of different parcels of air and the various cycles as the energy of the sun is dissipated around in the Hadley cells and the other cells that cycle energy through over the atmosphere. We've talked about processes of weather and different cloud formations and climatic regions and so forth. All of these sorts of processes of climate and weather relating to the atmosphere are ultimately powered by energy from the sun. And they involve interactions at the sort of surface of the Earth and above, although there's a lot of interaction with the oceans as well, which we haven't talked about yet, but there'll be episodes on the oceans coming up. So the point of this is that you can think of these sort of two processes of sun-powered, atmosphere-dominated processes, which is sort of weather and climate, and geoenergy-powered tectonic processes, sort of from the center of the Earth upwards to the crust. And where they meet is sort of where we live, right, on the surface of the Earth, the crust, the upper level of the crust and the regions on the surface of the Earth. What we're going to be talking about today and in the next couple of episodes involves how these two sort of processes interact with each other and how they sort of, the interplay between them. So this is particularly weathering, erosion, and deposition. I'll talk about more of each of those in a moment. The basic idea, however, is that the crust is being shifted around and moved and upthrusted and so forth by the tectonic processes and geothermal processes. But at the same time, it's also being moved around and weathered and eroded and redeposited by processes relating to the atmosphere and weather. So there's a constant interplay between these. If you want to think of it this way, you can think of it as if the tectonic forces and geothermal processes are putting the crust where it wants it, and the atmosphere, powered by the sun ultimately, is moving things around and putting the crust where it wants it. And generally the idea is going to be that the tectonic forces will thrust crust in particular areas. So they'll push up a mountain range, for example. They'll move an area of continental crust in a particular position. And weathering and erosion processes will tend to strip those down and move things down and sort of smooth things out so that everything is at a similar level. So you can kind of think of it as if the tectonic processes are constructive, whereas the atmospheric weathering processes are sort of destructive, although that's a bit of a simplistic way to think about it. But the point is to understand the interplay between these two sort of processes. And that really comes together at the level that we're talking about now, which is sort of geomorphology, which is how the physical geographic forms that we see, such as hills, streams, coasts, deserts, and so forth, how those are formed by the interplay of these tectonic geological processes on the one hand, and the atmospheric and meteorological processes on the other hand. So that's kind of what weathering and erosion is all about. Now, the distinction between weathering and erosion is that weathering just refers to the deterioration of rocks and soils through contact with water and gases, as well as biological organisms, although I'm not going to be talking about the biological component of it in this episode. So weathering occurs on a particular site with little or no movement. On the other hand, erosion can involve breakdown of rocks or soil as well, but it also necessarily involves the transportation of those materials by agents such as wind, water, ice, or gravity as well. So think of it as weathering is the breakdown of things, and erosion is maybe further breaking down, but also the transportation of that and the movement of that broken material away from the initial source to somewhere else. And eventually, that material will be deposited at some new location. So that's called deposition. So a simple example would be rain causing weathering of soils up in the hills, which is then suspended in a stream, which is then carried downstream. This would be the erosion process, and then deposited near the mouth of the river in a deposition process. So that would be a simple example of the weathering, the erosion, and deposition. But we'll see more examples of that going forward. So just remember that these three processes always sort of act together to break down and then move materials from one location to another. There are many different mechanisms of weathering and also of erosion, and that's kind of what we're going to be talking about over this series of a couple of episodes. Each key series of geomorphological features, such as deserts or streams or coastal features, can be associated with one or a couple of major weathering or erosion mechanisms. So, for example, streams, or rivers and streams, have characteristic behaviors of erosion that they engage in, which shapes how they are sort of structured and the patterns that we observe there. So in today's episode, we'll look at those. When we turn to looking at deserts, because deserts are dry, they are dominated more so by wind processes, and so we'll look at those and how they lead to characteristic erosions and other features found in deserts. Similar as well, there are particular processes of erosion and weathering that occur along coastlines, and so those dominate coastal processes. Likewise with glaciers when we turn to those. So these different phenomena are associated with their own characteristic erosion and weathering aspects or patterns, which we will discuss in turn. So after we finish a discussion of weathering and different mechanisms of weathering and a little bit more about erosion, I'll talk first about mass wastage or mass wasting, which is a very important mechanism of erosion, and then we'll talk about rivers and streams. In future episodes, as I said, we'll look at deserts, coasts, glaciers, and other mechanisms of erosion and their corresponding sort of geographical or geomorphological features. All right, so let's talk a bit more about physical weathering. So there's many different mechanisms of physical weathering. Remember, when we talk about weathering, that just refers to deterioration or breaking down, particularly of rocks, but it can also be soils or other mineral composites. And so this is not transportation, this is just the breaking down. And it can be distinguished into physical and chemical processes. Physical weathering involves only physical processes. Effectively, that means changes in temperature and stresses like forces applied to the rock or other materials, whereas chemical weathering involves chemical reactions. So first of all, let's talk about physical weathering. The four main types of physical weathering that I'm going to discuss are frost weathering, thermal stress, pressure release, and salt weathering. So let's go through each of those briefly. So frost weathering occurs in environments where there is regular freezing of water. And this is a form of mechanical process in which stress is created by the freezing of water into ice and then subsequent thawing and freezing again, often in repeated cycles, cause a wedging effect, which first of all begins in like very small cracks or gaps in rocks and then sort of expands them as the water enters it, freezes, it expands because ice is less dense than water, so it expands on freezing. This exerts a potentially very strong forces on the rock, which opens up the crack, and then it will later thaw and the ice is removed, but then it will freeze again and opens the crack further. So over the course of repeated instances or cycles of freezing, expanding, and thawing, this frost wedging process, as it's called, can open up cracks and actually completely disintegrate rocks. It's actually extremely powerful, this frost weathering process. It can take potentially many years, but it can be extremely disruptive, again, in environments when freezing of water regularly occurs. So the next type of physical weathering is thermal stress. So this occurs particularly in very hot environments like deserts. It involves the repeated expansion and contraction of rock due to temperature changes. So particularly like in a desert, you'll have a rock that's heated up during the day through sunlight. At night, then it cools down and shrinks, because most materials, including many rocks, expand when they're heated. And the expansion may only be a small percent or a small fraction of a percent, but it can still be enough to exert significant pressure on particularly surrounding rocks. So thermal stress is often quite effective, particularly when only part of the rock is heated. And so that part of the rock will then exert a force which causes it to expand only in one direction. So basically, if the rock is wedged in and is heated in one side, then it will expand out the side that it's not constrained in. And that will then cause cracking as it expands. And then it shrinks again, causing further weaknesses. And then again, that process repeated over and over again tends to weaken the rock and causes it to shatter and break into pieces. So that's thermal stress. The next form of physical weathering is pressure release. So this is a form of weathering that occurs when rock that is formed deep underground, particularly igneous rock, like granite, although it really can be any type of rock, but when these rocks are moved up to the surface by, say, uplift and erosion of overlying materials, eventually they reach the surface or close to the surface. The removal of overlying material reduces the pressure on the upper side of the rocks, and when that occurs, they expand, right? Because the pressure's been released on them on one side more than the other, and that causes, again, it's sort of similar to the thermal stress, except in this case, it's not temperature that causes the expansion, it's the relief of overlying pressure. That causes expansion of the rock, which again causes cracks and fractures to form along the stress surfaces. And particularly in the case of a pressure release, this tends to occur kind of parallel-ish to the surface. And this leads to sheets of rock breaking away and then being eroded away over time. This process is called exfoliation, and you can see if you Google exfoliation granite or something on Google Images, you'll see images of these sort of sheets of rock just breaking off granite. It's very sort of compelling because you think about how hard granite is, right? But this relief of pressure can actually just cause it to worn away in these sort of sheets. Now, the final form of physical weathering that I'm going to talk about here is salt weathering. This is caused by growth of salt crystals. So it's sort of similar to frost weathering, except instead of exerting pressure by freezing, in this case, the pressure is exerted by the formation of salt crystals. So this particularly happens in either desert environments or along coastlines where there's more salts available. So water will deposit into cracks, and then the water evaporates, depositing salt crystals. Over time, as the rocks are heated, the crystals expand and put pressure on the surrounding rock, causing it to splinter and sort of be wedged open. Again, similar to frost weathering, except in this case it's caused by salt crystals instead of water crystals. So those are some of the main mechanisms of physical weathering: frost, thermal stress, pressure release, and salt weathering. Remember, all of these, because they're weathering processes, only involve breaking up and breaking down of material, particularly rocks, in a specific environment. You'll notice that none of these processes really cause the movement of the material any significant distance. Again, the movement of the material is part of erosion, which we'll talk about later. So, having covered physical weathering, now let's talk about some of the mechanisms of chemical weathering. Chemical weathering being distinct because it involves chemical reactions, so actual changes in molecular structure, forming or breaking of bonds between different atoms, that gives rise to a disruption of the structure of particularly minerals that form the rock. And so, again, 4 main types of chemical weathering that I'll talk about here: dissolution, hydrolysis, oxidation, and hydration. And probably the easiest to understand is dissolution. So this is the process in which a mineral dissolves completely into a solvent, generally water. And so rainwater very easily dissolves many soluble minerals, such as halite or gypsum. But even something like quartz, again, which is quite resistant, can be dissolved by water given sufficient time. And so this is, the idea that water kind of eats everything in the end, right? It will eventually wear away and even dissolve basically rock if it's given enough time. Quartz and many other minerals as well are largely made of silica, and so these silica molecules can be dissolved by water with sufficient time. It doesn't happen quickly, of course, but over thousands of years, that is a mechanism by which the surface of a rock is gradually sort of worn away. Now, the next mechanism of chemical weathering is hydrolysis. This is sort of similar to dissolution in that obviously it involves water. In fact, pretty much all of these chemical weathering processes involve water, except for, I guess, oxidation, but we'll come to that in a second. But in hydrolysis, only part of a mineral is taken into solution. So basically, hydrolysis here is a chemical reaction between the mineral and water in which the mineral is transformed into something else, such as a clay mineral, and then part of the original chemical components of the mineral are taken into solution. So an example of this is acid hydrolysis, in which you have protons from the acid effectively attacking the chemical bonds in the mineral crystals, gradually wearing them down. I'm not going to get into specifics of particular reactions here because I feel like that's a little bit more detail than we need to get into here. I may talk about that a little bit more when we talk about caves and karst topology, which is a very important example of this sort of process, basically of wearing away of rock through acidic interactions. But for the moment, that will do. And let's move on then to oxidation. So if you recall from the chemistry episodes that we've done, oxidation is the loss of electrons of one species to another. And in this particular case, oxidation is referring to the reaction of particularly metals in minerals with oxygen. Because oxygen has a high electronegativity, meaning that it has a strong grabbing power for electrons. So basically the oxygen in the atmosphere wants to grab as many of the electrons as it can get from particularly the metals that are present in many minerals that make up rocks. And so this can commonly happen in environments when there's sufficient oxygen, and often water helps the reactions occur as well. One example is the oxidation of iron by oxygen to form iron oxide in a wide number of minerals. And this gives the affected rocks a kind of reddish browny color, which, as you may sort of know from the case of rust in other cases, crumbles more easily. So this sort of iron oxide is not as robust. It tends to crumble and not form as a coherent surface, and that obviously contributes to breaking down of the minerals and thereby helps to weather away the rock. So the final type of chemical weathering is hydration. So again, this is sort of similar to hydrolysis and dissolution in that it involves reaction with water, but in this case, it's not the dissolution of the minerals into water, even the partial dissolution as in the case of hydrolysis, but it's actually the attachment of water molecules to the minerals on the surface of the rock. So, for example, iron oxides can be converted into iron hydroxides by the hydration, effectively the incorporation of water molecules onto and partly into the surface of the mineral. Now, this disrupts the surface, making it more susceptible to various other further interactions, such as hydrolysis, or possibly dissolution, but a particularly hydrolysis reaction. So basically, hydration is a sort of a preparatory stage to further disruption of the surface. Essentially, any process that disrupts and disorders the crystal lattice at the surface of a rock is going to contribute to its ultimate weathering away, because that's going to increase its susceptibility to various other chemical or physical weathering processes. Remember that crystals which form rocks have an orderly or relatively orderly arrangement of atoms, and disruption of that orderly array through any type of chemical process or physical processes as well will ultimately lead to disruption of that structure and then gradual weathering away and decomposition of the rock. So that's a brief discussion of some of the main mechanisms of weathering, physical and chemical. And now I'm going to talk very briefly about some of the main aspects or mechanisms of erosion. Now, this is a much bigger topic because there are many more mechanisms of erosion than there are weathering. Partly that's because there are so many different environments in which erosion occurs. Whereas the weathering processes can occur, I mean, some of them were more like in desert environments, some of them more in glacial or water-rich environments. Erosion processes are more varied again because, as I said, you've got coastal processes, you've got your glacial processes, you've got your river processes, and all of these are quite complicated in and of themselves. So there's a lot more to say. Also, erosion is so directly related to the process of landform formation that we also want to discuss, well, I want to discuss geological formations and different aspects of physical geography in the context of the erosion processes that dominate those. So that's why we're going to spend more time on erosion than on weathering. But of course, the two processes are directly related. So as I just said before, erosion is the action of surface processes, so surface of the earth that is, such as water flow and wind in particular, that removes rock and soil from one location and then transports it to another location. The process of erosion is distinct from weathering, as I said, because weathering is only the process of breaking up rock or sometimes soils and other materials at one location without any transportation. Erosion always includes transportation. It can also include initial sort of breaking up processes, or those initial breaking up of the materials could have been caused by weathering. So the breaking up of materials can be a weathering process, which is followed by erosion, or erosion can include the initial sort of breaking down and the removal. That occurs in examples such as erosion by river and wind abrasion in deserts. Those are two examples where the breaking down of the material occurs in the same process as the removal of that material. Whereas, as I said, in other cases, they occur separately. There's the weathering, and then there's the erosion. In either case, deposition is a separate third process, which is the ultimate depositing of that material in a new location, often a location that is closer to the ocean and closer to the surface of the Earth, generally, because things are moving, down in accordance with gravity. Now, erosion is a natural process, and it's been present on Earth pretty much forever. However, human activities in the last few centuries have dramatically increased the rate of erosion by at least 10 times and maybe more than that. Mechanisms by which humans increase the rate of erosion include removal of vegetation, because vegetation helps to reduce erosion, agricultural processes, which disrupt soils and obviously often involve removal of vegetation as well, construction work, mining, interference with rivers like dam building and so forth, and many other mechanisms as well. So humans are a major contributor really the major contributor these days to erosion. Now, I've sort of mentioned these before, but I'm going to go over them just briefly again. That is the main mechanisms of erosion. It's maybe a little bit, it's not quite right to call these mechanisms. They're more like groups of processes than specific mechanisms. So it's a little bit different to what I just talked about with weathering. But nevertheless, this is a helpful way to organize the complexity that is erosion, and as well as to form a framework that will be helpful for thinking about the processes that we're talking about over the next couple of episodes. So the first two processes of erosion that we're going to look at in this episode are mass wasting and hydraulic processes, or basically river processes. Mass wastage is the process in which rock or soil falls or drops under the force of gravity. So think landslides or rock falls. That's what mass wastage is, and we'll talk about that in a moment. Hydraulic processes are those relating to rivers and streams, including erosion and transportation of those broken down materials by rivers. So those we'll look at today. In a future episode, I will look at aeolian processes, which is basically air-based erosion processes, which are particularly dominant in deserts, obviously, because there's no water there, or very little water. And so that's things like wind abrasion and so forth. Rainfall and surface runoff is also an important cause of erosion, and this are also going to be important in deserts, because although they don't get a lot of rain, when they do get rain, often there's a very substantial erosion that occurs because there's a lack of vegetation and so forth. We'll talk about that later in a future episode. Rainfall and surface runoff also leads into the topic of groundwater, which I haven't discussed before, and so I will try to fit that in there as well. And that's a very important factor for the vegetation and ecological structure of a region. Finally, probably in the third episode in this series, I'll talk about the last two sort of processes or mechanisms of erosion, which are coastal processes of erosion. So that's, beaches and cliffs and so forth. And glacial processes, which are a huge, interesting topic in their own right, and quite unique because they involve erosion in the solid state, which is relatively unusual. Mostly it's liquid water or it's the atmosphere, which is a gas. And as I mentioned before, all of these sort of separate processes are critical for shaping the geomorphology of particular regions. So deserts are dominated by aeolian processes, like wind processes. Many floodplains and other relatively wet temperate regions are dominated, at least in part, by the hydraulic processes, so the location of rivers and streams throughout those areas. Coastal processes obviously are responsible for the shape of the coasts and the landscape sort of patterns around there, and the shapes of the specific shapes of the continents and islands and so forth. Glacial processes are obviously very important both in mountainous areas as well as in polar regions. If you sort of put all of these aspects together, which we can class as erosion generally, but putting them together, it really explains a large portion of the geomorphology of the surface of the Earth, really. So that being said, let's now jump in and start talking about mass wasting or mass wastage, also called mass movement. Now, this is a general term for movement of rock or soil under the force of gravity. So, I mean, I suppose gravity is a force everywhere, but this is specifically dominated by gravity. So, in this case, the debris that's transported by mass wasting is not incorporated into another medium like water, wind, or ice. So that's what differentiates it from these other processes. It just falls or slides under gravity. No water or wind or ice needed. Mass wasting is often the first part of the erosional process, not always, but in many cases, because it involves initial breakdown and transportation of materials, particularly in mountainous and hilly areas. That's obviously where the force of gravity is sort of most significant, because the slopes are steepest. Needless to say, mass wasting involves moving material from high elevations to low elevations, because, that's how gravity works. And often what will happen then is other eroding agents, such as streams or glaciers, can then pick up the material and move it to even further elevations. But typically, mass wasting will sort of start the process. Now, there are many different mechanisms, like specific types of mass wasting, which I'll go through briefly in a moment. But before I talk about those, I just want to mention a concept called the angle of repose, which is sort of important for understanding this. The angle of repose is the steepest angle relative to the horizontal plane at which a material can be piled up without starting to slump, like slide down itself. So anyone who's tried to build a sandcastle will know what the angle of repose is. Basically, if you try to put very dry sand, like fine and dry sand, in a pile, it doesn't pile very well. And the way to describe that is that it has a very small angle of repose. You can't pile it up very nicely. It spreads out too much, right? Angle of repose can be increased through two main methods. One is larger composite particles. So basically, coarser grains of sand or pebbles, indeed, are even better, right? If you imagine stacking pebbles on each other, you can have a steeper angle than you can for fine sand because they don't slide over each other. They kind of get caught on each other and provide friction more easily. So coarser particles increases the angle of repose. The other thing that increases the angle of repose, as again, anyone who's trying to build sandcastles knows, is wetting the sand. So wet materials typically are much easier to sort of stack and have a steeper angle of repose compared to dry materials. In fact, sufficiently moist sand has effectively like a 90-degree angle of repose. You can basically make it vertical. Although if it's not quite wet enough, maybe it will slump a little bit, right? Now, there is an interesting phenomena in that if you add a small amount of water to it, what that will do is the water will percolate into the pore spaces between particles and help to sort of stick them together. So that's why it increases the sort of forces between them and will increase the angle of repose so that it can sort of stand up more steeply. But if you add too much water to it, depending on particle size and other factors, that can actually saturate the pore space so that instead of being filled with air, which is what the pores are, it's bits of air between the particles at a microscopic level, instead of being filled with air, the pore spaces are entirely filled with water. And this is called water-saturated sand or soil or whatever. And this saturation actually allows the particles to flow around each other. And this actually dramatically reduces the angle of repose. So this can happen in some cases if soil becomes saturated, it will actually start to flow. And that can obviously be bad news for any structures that are built on top of that soil. Anyway, so that's relevant. This concept of the angle of repose is relevant when we're thinking about mass wasting, because different processes will be dominant depending on the angle of repose, depending on the water content of the soil or other particulate matter, as well as depending on the mass of material and other local factors. So let me just go through a few main types of mass wasting. And one is that begins at the sort of slow level is soil creep. This is the slow downward progression of rock and particularly soil down a shallow slope. Soil creep is particularly exacerbated in the case of, that I just mentioned, water saturation, where the particles of soil or sand can basically start to flow around each other, and therefore very wet soil environments can flow quite readily. But even if that doesn't happen, over time, the soil will basically creep downhill. It gives rise to very interesting phenomena where you have sort of bending of the fences downhill. You'll tend to have cracks and falling debris on top of like roads or other flat structures. You might have trees that you see have a sort of a curved trunk because they started to grow perpendicular to the ground, but as the ground sort of moved under them, they start growing like directly upwards towards the sky, so they sort of curve a little bit. And you might have other structures or gravestones or other things that are bent or fall over as the creep gradually sort of moves downhill. So that's a particularly slow form of mass wasting, but it still counts as mass wasting because it's primarily determined by the force of gravity. Basically, the soil is being pulled downhill. And it mainly occurs in unconsolidated material, that is like soils or particulate matter. The difference between soils and like loose unconsolidated material, which is technically called alluvium, is that soil has a significant quantity of organic matter component to it, whereas like alluvium is just sort of like sand and things like that, or silt or clays and things. Again, depending on the size of the particulate matter, look back at the previous episode on rocks and minerals where I talk about that. But in this episode, the distinction between like soil and alluvium is not massively important. So sometimes I might just say soil when really the content of organic matter is not critical here. We're just talking about unconsolidated, like broken down particulate matter that's not consolidated like a rock. Anyway, so that's earth creep or soil creep. Now, another form of mass wasting is slump, or a debris slump, or a debris slide. There's different names for it. This involves the movement of a coherent mass of loosely consolidated materials a short distance downslope. So it's kind of a bit like creep, except it's more sudden, or typically more sudden, so it happens a bit more rapidly. And instead of like sort of gradually sliding downhill, there's a whole region that kind of slumps. It's sort of like if you stand up against a wall and allow your feet to slide out in front of you, you kind of slump downwards, right? It's sort of a slightly rotational as well as sliding downwards. A little bit hard to explain. If you sort of see a diagram of like soil slump or earth slump or debris slump, you'll get the idea of it. But it's movement of a more consolidated mass of soil, like a coherent mass of soil, but still unconsolidated, like it's not rocks. So it's a little bit more rapid than soil creep, but still not terribly rapid. Then we have earth flow. Earth flow is part of a sort of category of mass wasting mechanisms, which includes debris flow, mud flow, and rock slides, which are all more or less the same. The main difference is just how consolidated the material is and how saturated with water the material is. And so these all involve flow of material down a slope, typically a steeper slope than in the case of soil creep, and it happens more rapidly, so there's higher velocity here. So instead of very slow, like soil creep happens at like centimeters a year, earth flows or rock slides or mud flows can happen much more quickly, so like a few kilometers an hour, but not full-on avalanches. That's the next level, right? So sort of creep, and then there's sort of flow, and then there's avalanche, which we'll get to in a moment. So these various forms of earth flow, mud flow, rock slide, and so forth, they're all sort of similar. Again, the differences will be how consolidated is material. So in case of rock slides, you see large, units of rocks that break off and slide down the slope, whereas earth flow is more like soil and unconsolidated material. Mud flow is similar to earth flow, except that there's going to be a higher water content there. And in different sources, you'll see a slightly different way of characterizing or breaking up these classifications, but they're all sort of broadly similar. Again, depending on how much it's sliding versus flowing. So a debris slide is sometimes distinguished from an earth flow because there's more of a sliding of the material rather than a flowing. That's going to depend on how large the particulate matter is as well as how saturated it is. But they're all sort of broadly similar. And then we move into the most, catastrophic or dangerous of the forms of mass wasting, which are the avalanches, as well as rock falls. So an avalanche is a very rapid, chaotic passage of either consolidated or unconsolidated material downslope. So that can happen at many, many kilometers an hour. And there's a lot of sort of air and dust involved as well, typically, whereas slides typically don't have so much because the volume of material and the speed at which it's falling is not as high. So a debris avalanche has a lot of unconsolidated material, whereas a rock avalanche has more rocks and a mixture of earth in with that. Rock fall is the extreme case where you basically just have rocks falling straight down into like a canyon or something, or over a cliff. So there's not really any sort of sliding as there is in like an avalanche, but it's just sort of falling straight down. Those can be obviously very dangerous for anyone who's below. And the real difference between avalanche and a slide is sort of as I said, how chaotic the motion is, how rapid it is, as well as how steep the slope is. Again, avalanche is typically on the steepest of slopes. So that gives you an idea of sort of the range of types of motion here. It's all broadly the same in the sense of it's earth and rock falling down a slope or sliding down a slope on the basis of being pulled by gravity. But there's distinctions on the basis of how steep the slope is, how fast it's moving, whether it's consolidated or unconsolidated, whether it moves as a single unit or as flows or other factors like that. Now, there are many different triggers that can cause mass movement. Ultimately, of course, gravity is the sort of key defining factor here. The stuff's being pulled down by gravity, right? So that's the same everywhere. But the initial triggers can vary depending on the circumstances. So earthquakes are a very common trigger, right? There's an earthquake which can trigger an avalanche or a rockfall. But many forms of triggers are also non-natural. So disruption of the sediment or of the slope, say by potentially high rainfall, could cause disruptions, but also by construction work, and that's particularly common these days. Volcanic eruptions can also trigger rockfalls or landslides. Saturation of the slope material, so I talked about that before, how saturation actually reduces the sort of forces binding it together, or can reduce the forces and therefore cause it to sort of flow. That can also be a cause of mass movement processes. And another thing about these sort of mass movement processes is that they are typically sort of self-sustaining. So once part of the soil or some rocks start to fall or start to slide, then they'll hit others, right, which then exerts a greater force on them, which may push them over the edge, and then they start to fall, right? So there's sort of a positive feedback processes in this way. So initially they can be triggered by shocks such as slope modification, earthquakes, volcanic eruptions, or just prolonged rainfall. Undercutting by streams or coastal erosion is another factor, especially that can cause rockfalls if it's on the coast, where you get sort of a critical level and the forces pulling the rocks down exceed the forces keeping it in place, and then it falls or slides down the slope. Okay, so that concludes the discussion of mass wasting or mass movement that I wanted to cover. And the second part of this episode third part, I suppose, will now cover rivers and streams. So this might seem like it's a bit of a shift, right? But remember that all of these different topics are mechanisms or aspects of erosion. So the first we talked about was mass wasting, and the next we're going to talk about are hydraulic processes which occur in rivers and streams. Other processes we'll look at in future episodes. So here we're going to cover rivers and streams. Now, a stream is, in geomorphology, defined as a continuous body of surface water which flows within a bed and between banks. So basically, a stream is just a river. River is probably the more common colloquial term, at least in English, but typically in everyday English, we would use the word river to describe a larger stream, and one that is longer. Whereas smaller streams you might call streamlets, brooks, creeks, or a myriad of different other words. But in geomorphology, a stream is any of these things, as long as it's a flowing body of water on the surface that has like a bed and banks, and that is fairly regular. So that can also be seasonal, because some will only flow at certain times of year, but it sort of has a regularity to it. Then that's a stream. So there's a few key sort of pieces of terminology that we need to understand streams. Often we just sort of think about them as, well, they're just part of the world, right? There's just sort of rivers around the place. But there's actually many important processes that are occurring here that are very interesting to understand and helps to understand why the land is the way that it is, right? So the first thing to talk about in the case of streams is stream gradient. The gradient of a stream is basically how steep it is. So when we talk about the gradient of a stream, it's always defined relative to what's called the base level of that stream. So typically the base level is going to be wherever the stream is outlet to. So often that's the ocean, right? But there are some streams that outlet to, like inland lakes, and so that might be the base level of that stream. Now, you can also talk about base level in more relative terms, like you can just sort of define a particular part of the stream as a base level and then discuss relative to that. But for our purposes, we'll think about the base level as essentially sea level, or possibly the level of like an inland lake or something if it doesn't flow out to the sea. But most streams eventually flow out to the sea through other streams that they connect to. Now, essentially, what a stream is doing is a way of channeling water that's ultimately, of course, produced by rain. It's a way of channeling that water down out to wherever its outlet is, again, often the ocean, in the lowest energy way possible. So because everything effectively in the universe seeks its lowest energy state, water is doing the same thing as it flows from wherever it fell, like in the mountains or across plains or wherever. Eventually it percolates through on the surface or in underground water and finds its way into streams. Those streams then seeking the lowest energy state, trying to find as low a level as possible, and they'll keep going until they get to the base level. So a stream is a kind of a collective highway for the water to finding the easiest way to get down to the base level. So what streams tend to do, therefore, is erode through the bed. The bed is essentially the bottom of the stream, or the rocks or other material that it's on top of. The banks on either side of that. The channel is kind of the hollow bit of the land that the stream flows through, right? So the stream erodes through its bed downwards to achieve the base level of erosion throughout its course. So in other words, if we just had like one river that went from the headwaters, which is where it starts off, often up in mountains somewhere or hills, and down to the mouth at the base. If we just had that river and sort of nothing else, eventually what would happen is that the river or stream would erode down everywhere to the base level, or effectively to the base level. That often won't happen because there are other geological processes occurring at the same time, right? But that's what streams would tend to do. They try to erode everything right down. The rate at which this erosion occurs depends on the gradient of the stream. So basically, if the base level is very low relative to the headwaters, the stream will cut down very rapidly because there's effectively more energy available when there's a higher gradient and sort of more energy from the water falling down effectively. It will cut down very rapidly and erode rapidly. That also, of course, depends on the rock and the material that it's eroding through, depending on how resistant it is to erosion. Some types of rocks are more resistant than others. On the other hand, if the base level is fairly high, so that is the gradient of the stream is fairly shallow, then the rate of erosion will be much slower, and the stream will tend to meander, which we'll talk about in a moment. So the, I guess, arrangement or shape of a stream depends critically on its gradient and also the rocks and types of soil and other things surrounding it and that it's moving and that it's passing through. Now, I've sort of mentioned this idea before, but I'll just cover it again. There are two main types of channels that streams can pass through. So bedrock channels are composed of compacted rock and only small patches of alluvium. So that's like soils and sands and things. An alluvial river, which is typically more common, is one in which the bed and banks are made up of like sediment or soil. So again, probably we're mostly familiar with alluvial rivers. Bedrock channels are more common in maybe like a desert environment where there's not a lot of loose sediment because that's carried away and not held together through moisture and or plant material. So, think about the Grand Canyon. That's basically a bedrock channel because it's just mostly compacted rock. So that's important for understanding the erosion processes, of course, because how easy it is to erode depends on the material that you're eroding through. In addition to the nature of the type of channel, there's also the patterns of the channel. So this is effectively what the river looks like, so to speak, or the course that it takes, maybe another way to put that. There's sort of three main types that we'll talk about here: straight channels, braided rivers, and meandering rivers. A straight river is one that goes, well, you guessed it, kind of straight. So typically, these are relatively rare, but they occur more often if the stream is near the start of the stream where it's closer to its headwaters, so where it originates, often in a mountain or hilly region, and is progressing sort of rapidly downhill. Those sort of streams tend to be straighter, relative, or other things being equal at least. They don't meander very much. We'll get into that in a moment. And partly that's because they have a lot of energy, so they can just erode through stuff that gets in the way effectively, and they'll just sort of go straight down the path of least resistance, so to speak, and easily erode through sort of things that get in the way. However, typically straight patterns don't last for very long because as soon as the stream loses even a little bit of energy, it will, instead of just sort of eroding straight through like a bunch of rock that's in the way, it will tend to go around it, right? Because that's the least energy process. The more energy the stream has, which depends both on the amount of water there, but also on its velocity, which is determined ultimately by the gradient of the stream, then the easier it is to sort of just erode through things and go sort of straight through. Whereas as you lose that energy, which happens typically as the stream moves downhill, the slope tends to flatten out as you move away from the headwaters and towards the transfer zone and towards the depositional zone. So that's sort of different zones of the course of the river, right? You gradually lose energy as the landscape flattens out. And at that point, you tend to get one of two different channel patterns. There's either braided rivers or meandering rivers. So I'll talk about braided rivers first. The name is very good because it sort of indicates what it looks like. It's a sort of a network of river channels that are separated by small, often temporary little islands called braid bars. And these braided streams tend to occur in streams that have very high sediment loads. And so when they move from the steeper slopes down to the shallower slopes, a lot of that sediment comes out. We'll talk a bit more about sediment load in a moment, but that's the solid material that's suspended in the stream. A lot of that comes out of the stream because there's not enough energy to hold it anymore, and so that's deposited in this region of the braided stream. And then there's interconnected channels that move through the sediment, the braided bars. And so a braided stream looks like it's a bunch of little streams that are interconnected between each other, kind of like, I don't know, blood vessels or something. And typically these braided rivers are associated with streams that have a rapid and frequent variation in the amount of water they can carry. So if there's an increase in the amount of water, then the braided structure may be sort of occluded because there's a massive increase in the amount of water that you see there. Whereas when that decreases, you'll have the water level sort of lower, and then you'll have the braided structure, the braid bars become more evident as well as the sediments come out of the stream load and are deposited. So that's braided rivers. You also tend to see braided rivers around the mouths of rivers as they lose velocity, as they form a delta and intersect with the ocean often, or the wherever their base is. Now, the last type of channel pattern that I want to talk about is, I think the most interesting, is a meandering river. And that forms a sinuous path. So it's like a snake, snaking backwards and forwards in a kind of wavy pattern. Usually this occurs in fairly flat environments towards the end of the river, so often closest to the mouth of the river. And this occurs because by this point, the river has lost a lot of its energy, or the stream has lost a lot of the energy. And so instead of eroding through obstacles, it's going to go around them. And I'll talk a little bit more about that process in a moment. But first, I just wanted to define a couple of terms that I sort of briefly mentioned. One of them was a delta. So you're probably familiar with this term. This is a landform that occurs at the mouth of a river where it reaches the ocean typically, or sometimes like a reservoir or an inland lake or something like that. A delta it's sort of like a spreading out of the river, and also kind of maybe the floodplain surrounding the river. Deltas form from the deposition of sediment that's carried by the river. As the river reaches the mouth, it slows down dramatically because it's kind of reached the end, right? It's at the very lowest point that it's going to get to. And so a lot of whatever's remaining, the sediment is deposited. And then you often see this sort of braided structure, so this sort of braided stream structure at the very mouth. So people know about the Nile Delta as a very famous example of that. Another important concept, which is kind of related to a delta, is an alluvial fan. Now, this is a fan-shaped deposit of sediment that is built up by streams, and typically you find alluvial fans in canyons. So when you have a stream that is coming down from a very mountainous terrain and then emerges out onto flatter plains, that great reduction in the velocity of a stream reduces its ability to hold sediment, and so the sediment comes out of the stream and piles up in these big alluvial fans. And so you can sometimes see these even after the streams have dried up, or in a season where there's not a lot of water. You'll see these just basically huge fans of sediment just piled up at the mouth of a gorge or at the opening of a canyon or something. You can look up pictures of these. It's very very compelling. It's like someone like a huge giant just dumped a bucket of sand somewhere in the desert. It's very interesting. Anyway, but those are two terms that are useful to know. Now, let's come back and talk a bit more about meandering streams. So, as I said, a meandering stream, it has a single channel, so it's not the same as a braided stream, which has like many interconnected channels. But it winds in a snake-like way across its valley. Typically, the zone within which the meandering stream sort of shifts, because it's sort of moving, is known as the meander belt. And typically that's like 15 to 20 times as wide as the channel itself. So there's a sort of a range that the stream will meander and wander across, but it's sort of not unlimited, right? It's constrained to a relatively small region around the channel itself. Now, when we talk about a meander, that's basically a region where the stream sort of goes out one way and then comes back. It sort of wigs and wags out, if you like, in a sort of an S curvy pattern. So each one of those is a meander. Those meanders are not static, but they change over time, and they tend to move downstream over time as well. Effectively, these meanders are formed in a positive feedback process. So what happens is that there'll be some initial cause for the river to curve ever so slightly or move around some obstacle. Often it'll be some massive rock that's slightly harder to erode or something like that, right? Or maybe some small piece of elevation. So that causes a small curvature in the stream, right? Now, if there was high enough velocity, it would just sort of barrel through that. But because this occurs when the river has lower velocity, it doesn't have the energy to do that. So it goes around, and this forms a small meander. But this is the key point here. What happens then, and this is actually quite complicated in terms of the fluid dynamics, which I won't try to get into here, but the basic idea is that whenever you have a curve in a stream like that, the far side of the bend will tend to be eroded away, whereas the inner side, like the elbow of the bend, think about the inside of the elbow and the outside of the elbow. The outside of the elbow, think of that as the far side of the riverbank where the water is sort of moving around. That tends to be eroded away, whereas the inner side of the elbow, there tends to be deposition at that point because the water is traveling a bit faster when it's sort of eating into, when it's being pushed back by the outer curve, whereas on the inner side of the elbow, the velocity is slightly less there, and so the sediment load is reduced, and there tends to be deposition at that point. So this is a positive feedback process whereby when you get a bend, that the outer part of the bend tends to be eroded and the inner part tends to have deposition, which causes an increase in the curvature and which basically makes the bend even more. And so this is the positive feedback process. When you have some curvature of the stream, it tends to reinforce itself and become curvier and curvier. And that's how you get these very big meanderings. So that depositional feature which occurs at the sort of inner side of the stream is called a point bar, which you tend to see a deposition of sediment on the sort of inner side of the elbow, if you like, about where streams curve around. Over time, what tends to happen is that these meanders become more and more meandering and sort of curvier and curvier, until what can often happen is that at the base, it kind of like pinches off. If you imagine sort of pinching some skin and then sort of pushing your fingers closer and closer in together, and eventually, you can't actually do this, right? But if you imagine pushing your fingers together such that your like fingertips are touching, you would have actually detached the skin from your from your hand, right, or from wherever you're pinching. So that's kind of what happens with the stream. The curvy bit actually gets entirely pinched off because the stream kind of finds a shortcut. Often if there's a flood or something like that, it kind of realizes, oh, I don't need to curve around this part. I can actually just go straight through. And that's called a meander cutoff, where it kind of cuts off the meandering part and then just straightens up at that particular local region. Now, once this meander cutoff happens, the region of the cutoff that's left tends to become separated from the rest of the stream and form what's called an oxbow lake. So this is kind of a U-shaped lake or pool that forms when there's been a meandering, but then it's been cut off. And that creates a freestanding body of water, which is an oxbow lake. Or in Australia, these are called billabongs. Oxbow lakes don't have running water flowing through them, so they're still lakes. And so what tends to happen over time is that they eventually become like boggy or swampy marshes, and then eventually they'll evaporate completely because there's no regular flow of water through them. And you can actually see the landscape surrounding meandering streams, particularly the Mississippi, for example, which is an example of a meandering stream, closer to its mouth. If you see aerial photographs of that, I'd recommend taking a look. You can see the current stream and its meanders, but you can also see many oxbow lakes that have been produced and some sort of scars in the landscape where you can see there was an oxbow lake that subsequently dried up. There's a name for that. I've forgotten what it is. But anyway, it's very interesting to see and to understand how this is all part of the process of the river, basically trying to seek its lowest energy path down to the base level. So what you tend to have, as I said, is a process of meandering, which eventually becomes so meandering that it pinches off, forming an oxbow lake, which then gradually dries up, and then the meandering constantly changes. So rivers are not fixed, right? They're very dynamic and they're constantly changing. Not only can the whole course of a river shift, famously the Yellow River in China has shifted its course by hundreds of kilometers, many times even in historical time, like last few thousand years, but also its very shape changes with the meandering and the cutoff of oxbow lakes and things like that, as with floods, and the elevation of the river also tends to change over time. So initially there tends to be a sharper slope or a steeper slope, which eventually is gradually eroded away by the river, which then tends to become flatter, and in its older age it tends to sort of meander out more over a floodplain. Floodplains are more flatter and are associated with meandering streams because flatter territory is associated, right, with less energy for the stream, right? So it tends to then meander more. So that's a bit of a discussion about the channel patterns with a focus on meandering streams. There's another thing that I wanted to talk about which is related to this, and that's called a drainage basin. Now, there's a bit of a difference in terminology here. So we've actually talked about drainage basins before in the context of large regions of the Earth's surface that all drain out to a particular ocean. So much of the eastern part of the continental US, for example, either drains to the Atlantic Sea to the east, or it drains through the Mississippi to the Gulf of Mexico in the south. So those are examples of drainage basins, and often mountain ranges separate drainage basins. One side of the mountain will drain into this ocean, the other side will drain into the other ocean, depending on the direction. So that's a drainage basin. A drainage basin can also sometimes be used to describe the particular pattern of tributaries and branches of streams, although the phrase drainage system is also used here. So I think that's probably better because it distinguishes it from a drainage basin. So this is basically, what is the shape of the tributaries of a river? And again, if you've looked at rivers on maps, you might have just sort of taken it for granted that, well, that's just sort of what it looks like, right? But actually, there's a lot of reason as to why streams adopt the particular drainage system that they do. So one of the most iconic is called a dendritic drainage system. This is where you have, it's sort of like a tree-like structure where, one branch produces smaller branches, and that branches off into smaller branches again, and that smaller and smaller, and it's sort of like a fractal structure of breaking up into smaller and smaller. This is quite common, and they're typically found in a wide range of areas where there's relatively uniform bedrock and not too much of a steep slope or other unusual circumstances. So sort of your standard stream pattern just kind of branches out in accordance with basically the easiest way for the water to get downhill and to move towards its base level. But there are more sort of, not complex necessarily, but more characteristic drainage systems as well. A parallel drainage system occurs when you have linear slopes, like basically steep mountain slopes. And you'll have a number of streams that are just kind of running next to each other, all going downhill. And the reason they don't form a dendritic shape is because that whatever local impetus there might be to move slightly to like the east or west or whatever, in order to get around a particular rock, is overwhelmed by the fact that they're just going to go straight downstream, like north or south, if you think of it that way, right? So they're just going to go barrel straight through whatever local disruptions there are and erode through it. So that's where you tend to see parallel drainage systems. And there's steep slopes, they run swift and straight with few tributaries, and they all flow in the same direction. Rectangular drainage patterns develops when there are rocks that have fairly uniform resistance to erosion, but two different directions of jointing. So basically you can think of as like square or rectangular slabs of rock or minerals with kind of weak areas between them, gaps between them. And so the river tends to run along those weakened areas. So it might run like north to south, and then it'll go east to west, and then north to south again. So it's rectangular, very, very interesting pattern there. So highly jointed bedrock, where the bedrock itself is resistant to erosion, but there's joints between it where the erosion is much easier. So they'll have this rectangular pattern. A centripetal drainage pattern occurs when a number of streams converge on a particular point. So generally that occurs in a depression or a basin, or an inland drainage pattern where there's rivers that come down and terminate in an inland sea of some sort. The opposite of a centripetal drainage pattern is a radial drainage pattern, which has a central high location and the streams radiate outwards. So it's like a circular version of a parallel drainage pattern, I suppose. And that tends to occur particularly with volcanoes, where you have the very high central point and then the streams radiating outwards from that. Finally, there's a trellis drainage system, which is found in certain steep slopes of mountainsides. The difference here from a parallel one being that, so trellis patterns have a sort of a mainstream that's going down the mountain slope, but then they have some tributaries at right angles to them. And that can occur when there are certain formations, like rock formations in the mountain, where some are more resistant to erosion, and so you get the tributaries running in valleys along those erodible rocks, and then ridges between them of more resistant rock. And so you tend to have tributaries that specifically kind of carve out these channels in the more resistant rock and run perpendicular to the main channel, which then goes sort of straight downhill. So what's interesting here is that the structure of the rivers is really determined here by the slope, and as well as the type of rocks and materials and how sort of readily eroded they are. All right, so that finishes drainage systems, and we've talked about the channel patterns and the key features of the stream. There's just a couple of last little issues that I wanted to discuss before finishing out today. And one of those streamflow characteristics which we can sort of characterize as transportation of the eroded materials through the stream. So I've mentioned this before, but I haven't sort of given the key terms here. I've talked about, for example, the suspended load, or the sediment that's carried by the stream. Well, this can be understood as I sort of mentioned before, the solid matter that's carried by a stream. And streams can carry sediment or alluvium at various rates depending on the capacity of the stream. The capacity can be measured in terms of discharge. So discharge is the volume of water that flows past a given point per unit of time, and it's equal to the area of the stream multiplied by its velocity. So discharge increases as you have more water, and also as the water is moving quicker because of generally, again, a steeper slope. As discharge increases, you generally have wider and deeper rivers and that have a higher velocity. Rivers with a higher discharge will tend to also be able to accommodate a higher load of material, a higher stream load. Basically because there's more energy. There's more energy that's available to keep the load in the stream. And there's sort of three main different types of load in the material. There's the dissolved load, the suspended load, and the bed load. So the dissolved load is the proportion of, or the part of the stream's sediment load that is carried in solution. So particularly like ions, particles that have actually been dissolved, perhaps following chemical weathering, for example. So these are not macroscopically visible, but may change the color of a river, for instance. The suspended load is the portion of sediment that's carried by the fluid flow, which is sufficiently small so that it very rarely ever touches the base of the river, the bed of the river, but is not actually dissolved, right? So these are things like silt and clay, or maybe small sand particles. They're kept in suspension, but they're not dissolved, right? So they're separate from the water itself. They're not dissolved in like an aqueous solution, but they're fairly small, and you may or may not be able to see them with the naked eye, depending on how large they are and how turbulent the stream is. This suspended load is typically kept in suspension by turbulence, so the water moving around and sort of up currents and things like that keep it moving and very rarely hitting the bottom. The final form of stream load is the bed load, and this is material that slides and rolls along the bottom of the stream bed. It can also move along by saltation, which is basically a series of jumps. So there'll be some sort of turbulent flow of water, or maybe another rock hit a rock, which then pushes a smaller rock or a pebble or something up, and then that jumps a short distance and then lands downstream. And so a series of these sort of small hops, which is called saltation, gradually moves the sediment downstream. So typically, the larger the particles are, the larger particles are typically part of the bed load. Slightly smaller bed load particles will be moved by saltation, whereas the largest rocks will be typically moved by sliding or rolling. Smaller materials like silts and clays are part of the suspended load, and then individual ions or other molecular atomic substances will be part of the dissolved load. So it's basically just dependent on size there. So through a combination of the dissolved load, the suspended load, and the bed load, streams transport their stream load, so the sediment, alluvium, downstream. And as I said, the amount of load that a stream can carry is mostly dependent on its velocity and the volume of water that's in there. So that's why when it comes to shallower slopes, so a smaller gradient, then the sediment typically comes out of the stream and is deposited at some location, like in a braided stream, for example. Now, one final little topic is floodplains and river flooding. So I've mentioned these before, but just briefly, a floodplain is an area of land that's adjacent to a stream that stretches from the banks of the channel. So typically the river banks are where there's sort of a bit of a ridge on the side of the stream where there's deposited some material because of often during floods it deposits a little bit of material just around the edges. So those are kind of your river banks. They can also be sort of built up artificially as well. So the floodplain stretches from the banks of the channel to whatever base of the valley that encloses the stream. So it could be a small distance or it could be like many kilometers. Floodplains are kind of flat by nature, right? Because they're plains. And so what happens is during flooding periods, floodplains can be inundated by water from the stream. And they're regularly flooded, and then, as the flood subsides, the water level comes down. But during flooding, what happens is that the excess water spills over the banks of the river and then quickly spreads out over a very wide area. And as it does that, it quickly loses velocity and deposits whatever sediments it was carrying. So floodplains have regular deposition of nutrients that are often very useful for agriculture and crop growth, so that contribute to high soil fertility. In many agricultural regions are found in river floodplains, such as the Mississippi River Basin and the Nile Valley being two well-known ones. The downside to that is that because the river floods regularly, there's a risk to crops and livelihoods and any structures that are built on or near the river, especially if the levees, like artificial levees keeping the river within its banks or controlling flooding, are broken or not maintained properly. So this is a constant risk. And historically, there have been very large instances of river flooding, especially with the Yellow River, that have killed hundreds of thousands of people because of either improper maintenance of the levees or even sometimes deliberate destruction or opening of the levees. Floodplains are sort of many of the earliest civilizations, such as the Sumerians and Egyptians, the Indus Valley civilization in India and so forth, started up on floodplains because they have a ready source of water and nutrients for their crops, and also a means of transportation along the river. So there's a lot of good things there for sort of humans, but it does come at the risk of floods being destructive. Or the flip side to that is if the floods fail for whatever reason, then you're in trouble. But that concludes what I wanted to talk about this time. So we've covered weathering and erosion, mass wasting, and rivers and streams. In this series of episodes, I think we're going to talk about wind processes and deserts, and as well as probably we'll talk about groundwater and rainfall and surface runoff as well. So two other important processes of erosion and also landform processes. So hopefully you enjoyed this episode. If so, you might consider giving a positive review to the podcast on whichever podcast aggregator you prefer. If you'd like to make a suggestion or just give feedback on the show, please feel free to send me an email. My address is fods12@gmail.com. That's FODS12@gmail.com. If you would like to support the show financially, you can make a one-off donation via PayPal using my email address, or you can head over to Patreon and become a supporter for each small dollar amount for each show that I release. I really appreciate my small but loyal following of Patreon supporters, so that is much appreciated. And recently, I don't know if you can hear, I got a new microphone, which hopefully has improved the audio quality of the show. So thanks for assisting with purchases like that. So anyway, until next time, take care, and I'll talk to you then.